5. 1, 2, 3, 4, 5. Okay.
Alright, today we'll be talking about conditional statements, and a conditional statement is as follows. It is P implies Q, which can also be expressed as if P then Q, P is sufficient for Q, P implies Q, or Q whenever P. And the way the statement's set up is P would be your hypothesis to the statement, and Q would be the conclusion to the statement. So the truth table for this statement is as follows. So when P and Q are both true, then the statement will become true because a true hypothesis implying a true conclusion would be true. Where P is true and Q is false, the conclusion is false, so the overall statement is false. If the hypothesis is false but the conclusion is still true, the statement is still true. And if both P and Q, the hypothesis and the conclusion, are false, the statement is still true. So for example, if we had a statement that says, if it is sunny out, then we will go to the beach, then we could assign sunny to be P. I'll draw a little sun here for that. Oh boy, that's a really big sun. And if Q was going to the beach, I'm drawing a little set of waves here, then we could say if P is true, which means it's sunny out, and Q is true, which means we went to the beach, then the statement is true that if it's sunny out, we went to the beach. If it's sunny out, but you don't end up going to the beach, the statement is false because it says if it's sunny out, then you would go to the beach. If it's not sunny out and you still end up at the beach, the statement's still true. And if it's not sunny out and you don't go to the beach, this still somewhat proves the statement, which means it's true.
Alright, so now we're going to talk about three very important concepts when it comes to conditional statements. We have the converse of a statement, which is, assuming we have the original statement, if P, then Q, the converse is if Q, then P. The contrapositive of if P, then Q is not Q implies not P. And finally, the inverse of if P, then Q is not P implies not Q. Let's take this example. Let's say P is, if we go to the beach, Q is, then we pick up babes. So the contrapositive of if P, then Q is if not Q, then not P. Which makes sense, because if we don't pick up babes, then we did not go to the beach. The converse of this statement, the original statement, P to Q, is if Q, then P. This statement is saying, if we pick up babes, then we go to the beach, which is not necessarily true. The inverse of the original statement, if P, then Q, is not P, then not Q, which is saying, if we don't go to the beach, then we don't pick up babes. I mean, come on, we could have picked up babes at the arcade.
So let's go through biconditionals. By definition, biconditionals is P if and only if Q. And this is equivalent to P implies Q and Q implies P. So only when P implies Q is true and Q implies P is true, then this biconditional is true. So its truth table is as follows. We see here, if P and Q are both true or both of them are false, then P biconditionals Q is true. If one of them is false, then the statement is false. It makes sense because look at the second one. If P is true, Q is false, then P implies Q is false, so the biconditional is false. And if the third one, if P is false and Q is true, then Q implies P is false. So, because it is a conjunction of P implies Q and Q implies P, so if one of these is false, then the whole statement is false. So there are some other ways to translate this biconditional in English. One is P is necessary and sufficient for Q. There is also a shorthand notation, P, I, F, F, Q. IF here means if and only if. It is not a typo. It is just a shorthand notation. So that's it.
So for that, we're going to move on to a couple more examples now. This is problem number 32 in the book from the section. It's saying P is true if and only, so P if and only Q. It's using a biconditional. Biconditionals, just like normal conditionals, they're the ones that grew up, went off to college, and became a little bit curious, right? Anyway, so for this we're trying to figure out if this is true or false. And for this to be true, we have to have both P implies Q be true and Q implies P be true. But since they're the same variables, we have to have these same ones true on both sides. So if we were going to have this first one be false, we want to have true imply false, which makes this whole thing false. But then if we take those same values and put them down here, we have false implies true. This is actually true. That looks weird. This is true and this is false, and since these are not the same, that means the whole thing is false. Next problem is problem 31F on page 15. Conditional statements are really strong because when you have your truth table, you have true, true. Like you said earlier, they're going to be true 75% of the time because this is true, and this is true. So the only way for the entire thing to be false is if we have that set up right there. So we're going to say, okay, it's probably true, but let's see if we can make it false. So we come in, and since we want these two sections to be false, so we want to have true here and we want to have false here. And for this to be, that's ugly. For this to be false, we want to have this set true implies false. And so now we can go plug those in, which means true and false there. So false implies true is true, and then I'm gonna erase the truth table. False implies true is true, true implies false is false, and then true implies false is false. So the entire thing, again, is big, fat, false. That about wraps it up for conditionals. Again, look in the book if you have any more questions. There's a lot of good stuff in there, and I hope this was helpful. Thanks very much.